10 requests a second, everything's fine. 10,000 requests a second and the same server falls over. No errors in the logs, no bad deploy, nothing obviously wrong. Just dead. And nobody on the team knows why. I'm Kai, fun with learning technology, where we open the hood on the tools you use every day. Picture a library where a formula tells you exactly which shelf a book sits on. No searching, you just walk straight there. That's the deal a hash map makes with you. Hand it a key, get the value back instantly, no matter how big the library gets. Today's question, why does that deal secretly break, and how do real hash maps stop it from breaking? So how does a key turn into a spot in memory? Think of a mailroom clerk, hand them a package labeled cat, they run a quick formula on the label and toss it into bin number 2. That's a hash function. The number it spits out gets squeezed down to fit the size of your bucket array, and that's where the value lives. You don't need to know the formula, that's not the point of this video. What matters is one plain fact, 2 different labels can get tossed into the same bin. Here's the thing nobody escapes, there are way more possible keys than there are buckets. Cram enough pigeons into fewer holes, and 2 pigeons share a hole eventually. That's the pigeonhole principle, and it applies here whether you like it or not. When 2 different keys hash to the same bucket, that's called a collision and it's not a bug. It's math. Every hash map, no matter how well written, will hit 1. So what happens when a bucket already has a key and a new one lands there too? The hash map doesn't throw it away, it chains it. Each bucket becomes a tiny list, and every new collision just gets appended to that list. 1 key in a bucket is nothing. 50 keys in the same bucket means every single lookup there has to walk past 49 others first. In short, a hash map's constant time promise was never really about one lookup. It was about every bucket staying short. The moment one bucket's chain grows long, every operation on that bucket, inserting, finding, deleting, has to walk the whole chain. Your fast constant time map quietly turns into a slow linear scan, and it only takes one overloaded bucket to do it. Collisions happen by accident all the time, and hash maps shrug them off just fine. But what if someone causes them on purpose? This is called an algorithmic complexity attack. An attacker studies your hash function, then crafts a batch of keys that all hash to the exact same bucket deliberately. Send a few thousand of those in one request, and you've handed one bucket a chain from hell. Here's a question for you. What do you think happens to your server's CPU and response time once those crafted keys start flooding in? Drop your guess in the comments before the next slide. Here's what that looks like in actual code. This endpoint takes a JSON body from the request and uses whatever field the caller sends as a dictionary key. No validation, no limit on how many. I've shipped code exactly like this before, genuinely didn't think twice about where those keys came from. That's the whole vulnerability. Untrusted input becomes hash map keys unchecked. Now picture that endpoint under a normal day of traffic versus the moment those crafted keys hit. Ordinary traffic, low CPU, quick responses, nothing to see. Then the attack lands, one bucket balloons to thousands of entries, and every request touching that bucket has to crawl the whole chain. CPU spikes, response times go from milliseconds to seconds, and the whole server grinds to a halt, all from one dictionary. So what do real hash maps actually do about this? 3 defenses stacked together. First, randomized seeding. Pick a random hash seed at startup so an attacker can't pre-compute colliding keys against your exact function. Second, treeifying. Once a chain gets long enough, some maps switch that bucket from a list to a balanced tree, so the worst case stops being a full scan and becomes something closer to a quick search. Third, load factor limits. Resize and rehash the whole table before any one bucket gets a chance to grow out of control. If I had to pick one to never skip, it's randomized seeding, it's cheap, and there's no real excuse not to have it on. Stack all 3, and the attack that took your server down stops being a threat at all. So here's where we land. Collisions are unavoidable, pigeonhole math guarantees them, every hash map will hit 1. But an unbounded chain isn't inevitable, it's a choice, and it's usually the default until someone tunes it. That's the gap an algorithmic complexity attack exploits, and is the gap randomized seeding, treeifying, and load factor limits close. Next time your hash map surprises you under load, you know exactly where to look. You made it to the end, that's the hard part. Subscribing's easy. If something feels off or missing, Or you want to see something new? Tell me in the comments.